Thunder and lightning are common enough to be known to everyone. Primitive people thought they were signs of the anger of the gods. At times, sailors were afraid of a strange light they might see at a mast or spar end at night. They called it St. Elmo's fire. People who lived in the north saw the northern lights on cold evenings. All these things are examples of electrical phenomena, but man knew very little about electricity. In the 6th century before Christ, a Greek philosopher called Thales discovered something strange. He found that if he rubbed amber with a piece of fur, it would pick up little pieces of wool or fluff. He thought this was some kind of magnetism, but later it became known as electricity, from the Greek word for amber, electron. Early in the 18th century, a Frenchman named Dufay discovered that there were two kinds of electricity. One resulted from rubbing amber and other resins with fur, and the other by rubbing glass with silk. The unlike kinds attract one another. The like kinds repel one another. Not many years later, Benjamin Franklin proved by a dangerous experiment that lightning was electrical. He flew a kite in a thunderstorm and found that he could get a spark from a key fastened to its string. Franklin believed that electricity was an invisible fluid. He thought that when a substance contained the normal amount, it was neutral. If some of this fluid was taken from one body and given to another, the one with too little had a negative charge, and the one with too much had a positive charge. We still use these terms today, but it has been shown that it is the negative that moves. In Italy, a professor of anatomy called Galvani found a new way to produce electricity. He discovered that the legs of a dead frog twitched when touched with a steel knife, which was also touching a copper hook from which they hung. Another Italian, named Volta, realized that the movement was caused by electricity, produced when the metals touched. This gave him an idea. He made a pile of discs of two different metals, zinc and copper, separating the different discs with a piece of cloth soaked in salt water. He discovered that if you connected the top and bottom of his pile through wires to his electroscope, the little gold leaves in the bottle moved. An electric current could be produced from the same cell. He turned his pile into the first battery by putting the two metals into cups of salt water and connecting them together one after the other. The knowledge of electricity was beginning to widen. 20 years later, a Dane named Ørsted noticed that a compass needle near a wire through which current was passing moved. An electric current was having a magnetic effect. This gave an Englishman, Faraday, an idea. He reversed the process, moving a magnet through a coil of wire, and his instrument showed that a voltage was induced. This discovery was of the utmost importance to the world, for from it our modern generators have been developed. Faraday had given a start to industrial development. Now, electricity is one of our most highly prized daily servants. An intricate and complicated economic and social system has developed around electricity. The face of our land has changed. overhead cables carry electricity to the far corners of our nation. But however closely we look at these wires, we cannot see what is happening inside. Early in the 19th century, a scientist named Dalton developed the atomic theory. This was important to us because to understand electricity, we must know something about the composition of matter. Later scientists have expanded the atomic theory. Hydrogen, which has first place on the table, is a gas. It is one of the simplest elements. Uranium is one of the most complex elements and is among the last on the table. A piece of silver, like all other matter, is composed of countless atoms. It is impossible to see an atom, but experiments have shown what it must be like. In early days, it was believed that the atom was the smallest particle. Then, Sir J.J. Thomson and other scientists discovered there are even smaller particles. Millikan later measured the mass and charge of these particles. We now know what the inside of an atom is like. There is a central nucleus, around which other particles called electrons revolve at tremendous speeds, much faster than you could see. The nucleus itself consists of a number of particles, but let's think of it as a single unit which has a positive charge. The electrons move around the nucleus very, very fast and in all directions. But to make the picture clearer, we will show them all moving in one plane. Their paths are not circular. They move in figures called ellipses. But we will show them moving in circles because it makes it easier to follow what happens. The nucleus has a positive charge, and the electrons have negative charges. The positive charge on the nucleus is normally exactly enough to balance all the negative charges of the electrons. The hydrogen nucleus only requires one electron to balance its positive charge. Uranium, with one of the largest atoms, has a very different nucleus. Its positive charge is 92 times as great as that of hydrogen, and 92 electrons are needed to neutralize it. Copper is a metal much used as an electrical conductor. Let's see why. The copper nucleus has a positive charge sufficient to balance 27 electrons. The atom of one element differs from another in the size of the positive charge of its nucleus. The electrons around the nucleus are the same from one atom to another, regardless of what element the atom is. You might change around all the electrons, but you would not change the nature of the elements at all. They would still remain hydrogen or copper or uranium or whatever they might be. Copper has an electron which can be freed very easily from the atom. Let's see what happens if this takes place. If an electron is taken out of a copper atom, the atom becomes positively charged because it needs one more negative electron to make it neutral. And the negative charge of the electron is just sufficient to balance the positive charge of the rest of the copper atom from which it has been taken away. It is now neutral again. This diagram represents the atoms in a piece of copper. Each atom has one electron which is held very loosely. So loosely, in fact, that it can hardly be said to be held at all. The electrons wander about from one atom to the next. It's these free-moving electrons which make copper a good conductor. When a current starts, there is a movement of electrons. The electrons repel the electrons nearest them, which in turn repel others all along the conductor. movement can be started by chemical means, as in a flashlight battery, or mechanically, as at a power station. But the result is the same in either case. There is a flow of electrons along the conductor, and it's this flow which we call an electric current. As long as the stimulus continues, the flow of electrons continues. Let's look at a complete circuit. In an electrical circuit, we have a means of starting the flow of electrons, for instance, a battery. There are wires of copper or another good conductor to carry the current where it is required. The electrical effect is caused by a stream of negatively charged electrons which flows through the circuit. Now, to sum up, an atom consists of a positively charged nucleus which will counterbalance a definite number of negatively charged electrons. If for any reason an atom loses an electron, it is no longer neutral. It has a positive charge. The electron which the atom loses is negative. It is the movement of electrons that makes the electricity men use in their daily lives. This theory explains the things about electricity that men have been trying to understand since Thales made his first discovery about amber hundreds of years ago.